Bismillahirrahmanirrahim. Lecture number 13, combined cycle power plant with multi pressure. In a previous lecture, we did introduce the combined cycle, and the combined cycle is the combination of Brayton cycle and Rankine cycle. And we have seen that when combining them both cycle, we would be able to harness some of the waste energy which is leaving the stack and producing some extra power out of it. So the efficiency of the combined cycle is much better than the any efficiency of any of the cycle that is including in the combined cycle. Having said that, we have also done a numerical in which we have seen that the energy which is leaving the stack is still at the temperature which is around like 400 300 to 400 degree Fahrenheit. So that means like if a combined cycle, if the steam is generated at the pressure of, let's say for example, 90 bar and 300 degrees centigrade, so energy which would be leaving the stack would be still high enough, so we can still use that energy, or we can still harness that energy, and we can still produce some extra power out of it. So combined cycle with a multi-pressure steam reduces the temperature of the gas, leaving the heat recovery boiler, and hence that would result in the increase the efficiency of the power plant as a whole. So dual pressure cycle, as shown in this figure, is having two energy circuits. One is called as the high pressure circuit, and the other is called as high pressure circuit, and the other is called as the low pressure circuit. So in a high pressure circuit, high pressure steam is generated and which is expended in a high pressure stage of the turbine, steam turbine. And in low pressure circuit, low pressure steam is generated which is expended in a low pressure stage of the turbine. So we have got two pressure circuit, high pressure circuit and a low pressure circuit, expanding in different stages of the turbine, and that is the high pressure stage and the low pressure stages. So exhaust gas leaving the, if what is actually a theory behind, or what we have already done in a previous lecture. So if we have got a single pressure circuit in a combined cycle power plant, or in a single pressure circuit in HRB, heat recovery boiler. So what would happen, like let's say for example, the the gas which is exiting from the gas turbine at state number 4, let's say, it is heated in a supplementary firing at state number 5, and entering into HRB at state number 5. Now if we have got a single circuit installed in a HRB, so the gas would be leaving from the gas turbine, from the HRB at a temperature which would be above the temperature which we were expecting for the dual pressure. Or in other words, if I'm saying like if only one circuit is installed in HRB, so the gas would be leaving from HRB at a stage, let's say for example at 6 dash, and then from that steam would be entering into the turbine, then exiting from the turbine at 7, from the condenser at 8, and obviously so on and so forth. It will be into the pump and to the back to the HRB. Now, if I install another pressure circuit in it, so rather than gas leaving at 6 dash, it would be possible to extract extra energy from the gas into a low pressure circuit, and the gas which would be now leaving at the from the HRB at a temperature which would be less than temperature at 6 dash. So what happened over here is exhaust gases gas leaving the gas turbine enter the supplementary firing at 4 and leaving to the HRB at 5, which is again leaving to the stack at 6. Condensate leave the steam condenser at 8, enter into the condensate pump and 2 closed feed water heater and 1 open feed water deaerator over here, and then entering into boiler feed pump. Now let's talk about the after boiler feed pump. So in a boiler feed pump, this would be entering into a HRB, which would be at state number 10 over here. Now, at state number 10, it will be fed into the economizer. Then from the economizer, it will be fed into the boiler side of the steam generator. So if the steam is generated, it will be leaving the the steam drum, and if it is not generated, obviously it will be recirculated in a boiler. Now, if steam is generated, it will be leaving the boiler at 12 and entering into a superheater and then leaving the superheater at 13. Now from 13, it will be expanding into a low pressure stage of the turbine and back to the circuit. Now, if, as I said earlier, if the only one circuit is there, so the gas would be leaving at the temperature which would be higher than the temperature we would be expecting in a dual pressure, if I say. Now, in a dual pressure circuit, what happened, like, rather than the gas leaving at stick 6, we have added another circuit, and that's what we call it as a low pressure circuit. For simplicity, we have already said about the low pressure circuit, but let's check, like, or let's check the cycle now as a whole. So we have got a high pressure circuit of the turbine. Gas is entering into the high pressure circuit, and then after high pressure circuit, it is entering into a low pressure circuit. So obviously it's the same thing, but in a one go. So once gas enter into a high pressure circuit, the gas passes further on, and then obviously energy, some of the energy is harnessed in a low pressure circuit. So coming back to the cycle itself, so at 10 it is entering into HRB at a low pressure, and obviously if I'm just looking at the temperature profile, so at this point the temperature would be much higher, and at this point temperature would be lower over here. So gas, the feed water is entering at state 10. It is fed into economizer, and from economizer it is fed into the boiler, and then obviously to a steam superheater, and it is leaving at superheater at 13, which is fed into a boiler. Now in the high pressure circuit, what will happen, like, the feed water which is actually moving from 10 to 11, some of the feed water is actually moved forwarded, and the rest would definitely move into a low pressure circuit. The feed water which is actually moved forwarded is actually pressurized in a booster pump over here, and once it is pressurized in a booster pump, the pressure of the feed water would be increased, and it is actually fed into a high pressure circuit at state number 14. As from 14 to 15, it will be economizer, in which the temperature would be increased. From 15 to 16, it will be boiling, and from 16 to 17, it will be again superheating, and from 17, actually, it will be fed into a high pressure stage of the turbine, in which it will be expended to make a power. It will be much more easy if I would just explain in today on a TS diagram. So in a TS diagram, or sorry, TH diagram, if I write it, temperature, enthalpy diagram, temperature versus enthalpy or temperature versus energy. So if I'm drawing the TH diagram of any of the combined cycle, so it would look like the energy which is lost by a gas cycle, which is, let's say, for example 5 to 6, would be gained by the Rankine cycle, and that would be from, let's suppose, 10 to 11, 11 to, sorry, 10 to 11, 11 to 12, and 11, 12 to 13, let's say, for example, like this. So that means like the energy or the enthalpy which is dropped from the gas cycle from 5 to 6 is actually gained by the steam cycle from 10 to 13, and that is the change in the enthalpy over here. So same would apply over here in this multi-pressure cycle. So we have got the energy lost by the gas cycle from 5 to 6 dash, or let's say for example 5 to total 5 to 6. On in other words, if I'm not having a low pressure circuit installed, so I would be leaving at stack at 6 dash over here. So writing or drawing TH diagram for both of them, so it will be from, let's say, enthalpy dropping from 5 to 6 and enthalpy gain on the steam cycle from 10 to 11, 11 to 12, and 12 to 13. That would be in a low pressure circuit. And then another enthalpy, that would be from 14 to 15, 15 to 16, and 16 to 17 in a high pressure circuit. So that would make something like this. On a TH diagram, we are having enthalpy which is dropped from 5 to 6, and it is actually gain in a high pressure circuit from 14 to 15, 15 to 16, and 16 to 17. At 10, we are feeding into a feed water, sorry, a booster pump, and to 14. That's what actually we have written over here. Um, and then that is actually a high pressure circuit. By installing another low pressure circuit, we are getting enthalpy from 10 to 11, 11 to 12, and 12 to 13. So having said that, if I am having only one pressure circuit, and let's say that is actually a high pressure circuit only over here, so that the enthalpy would be only gained from 5 to 6 dash, and it will be only gained, enthalpy leaving in HRB by the gas would be gained by the steam cycle from 14 to 17, somewhere here. So that's what actually we are saying. So enthalpy which is dropped from 5 to 6 dash is actually gained by the high pressure circuit from this to this, and in that sense we are saying like the gas, if we do not have the low pressure circuit, the gas would be leaving at 6 dash. Now installing another pressure circuit which is low pressure circuit in the HRB, so we are getting another enthalpy drop in a gas cycle or from the gases, and that is from 6 dash to 6, and it will be gained by the low pressure circuit from 10 to 13. So by installing a low pressure circuit, we are getting the enthalpy which is a little bit more than the enthalpy which were previously harnessed. So in this manner, we are having efficiency which would be much better than the efficiency of a single pressure circuit or single pressure combined cycle. So it can be seen from the TH diagram that low pressure steam boil at a temperature at 12 degrees, at a point 12, below that of the high pressure which is at 16. So hence there are two pinch points between the gas line and the saturated steam line. The pinch point is the location in the heat exchanger where the temperature difference between hot and cold fluid is minimum at that location. That means like the location at which we are having a temperature difference which is minimum. So in that case, we are having these two pinch point over here from this, from the gas cycle and the steam cycle. So the more these pinch point are apart, the heat exchanger efficiency is less, and the more actually it is near to each other, the efficiency of the heat exchanger is more. So that is actually the pinch point. So adding the low pressure circuit allow the gas to leave at a temperature 6, thus extracting more energy from it and increasing the overall cycle efficiency. So example of a dual pressure combined cycle is Dongri Trottenberg, what they call it, plant of PNEM in Holland or Netherlands. It has gas turbine output of 76.7 megawatt and a steam turbine output of 47.3 megawatt and attain a remarkable efficiency of 46.1 with only one deaerator feed water heater. You can have a triple pressure cycle, but the triple pressure cycle are normally used in the reduction for the reduction of nitrogen oxide emission to meet the NOx standard, not RIG standard. Um, Now moving forward to a combined cycle for a nuclear power plant. A combined cycle for a nuclear power plant presuppose that gas-cooled nuclear reactor, which we call it HTGR, is the heat source for the gas turbine cycle. So what happened in HTGR is like the helium gas is used as a coolant for the nuclear reactor. So the nuclear reactor is cooled by a helium gas. By cooling, that would mean like the temperature of the helium would be increases and enthalpy of the helium would be increases. Then this high heated helium is expanded into the helium turbine, which would be actually again into the heat exchanger, or what we call it as the intercooler or the feed water heater, and then it would be actually fed into the compressor back and then expanded into compressor and then to the HTGR back. So that would be a closed circuit. Helium is actually not leaving the gas cycle over here, but we do have like such a combination that helium is combined with the steam cycle in at a point which we call at a point which we already know FWH, and which is feed water heater. So in at the start, what would happen, like the helium would be fed into the compressor, helium compressor. The pressure of the helium would be increased from 1 to 2. It will be then fed into the regenerator where it would be preheated. Helium would be preheated, and the reason for preheating helium is like it would be avoiding some thermal shock to the HTGR. Like if we are releasing cold, or if we are actually putting throwing cold helium on HTGR, it might have got some thermal shock, and it both not good for the helium itself and for the HTGR obviously. So we are having a regenerator in which we are the temperature of the helium would be increased. It is then fed into HTGR where maximum amount of temperature or energy would be actually absorbed, and then it would be fed into helium turbine, and then it will be expanded. From the helium expansion, turbine expansion, it is back into the regenerator. Uh, some of the energy is absorbed in a regenerator, while the maximum energy it would be actually gone into the feed water heater. Now coming into the steam circuit, or if I would say like the Rankine cycle, the bottoming cycle, there there would be a feed water which will be coming at 11. This feed water is fed into feed water heater where the temperature of the feed water would be rise high enough, and then it will be fed into the steam generator where steam would be generated and it would be fed into the steam generator, steam turbine, sorry. Rather than actually combining the topping cycle, which is the gas cycle, and the bottoming cycle into HRB, which was heat recovery boiler, and it was kind of a heat exchanger in which the steam was already made. So in this circuit, the feed water heater is used to absorb the energy from the gas cycle into the steam cycle. There are a few possibilities like why it is actually absorbed in the feed water heater rather than the steam generator. One of the reason might be like there would be both of the cases over here, the feed water, the in the gas cycle over here, the if we have got the helium, so that is in a gaseous form, and let's say for example if we actually put it into HRB, that would be same in a gas phase as well. So for a possibility like if for example or for God's sake like if any of the circuit is broken or the gas is leaked in any of the circuit, like for example if the steam is leaked into the gas cycle or the helium is leaked into the steam cycle, so both of the circuit would be damaged. So for that reason might be the feed water heater is connected to the steam cycle, so that can be possibly like if there is actually some disturbance in the circuit, so the gas would be leaked into the water rather than actually leaking back into the gas cycle, and that mean like saving the gas cycle which is actually going in the HDGR, which is the nuclear reactor. And in this case, the heat is only rejected in a steam condenser. Now, one of the most important topic nowadays is the IGCC, which is Integrated Gasification Combined Cycle, and that is Integrated Gasification Combined Cycle Power Plant, if we are based power plant on that one. So for over a decade, like the nuclear, the vapor power plants, they are fueled by coal, or now even the over a century now, the vapor power plant, sorry, is fueled by coal, and coal is the workhorse of the US electricity generation. Even like if you are looking for the UK electricity generation, still around 32% of the electric power is dominated by coal power. So now, due to the environmental concern and due to the carbon footprints of coal and due to the carbon degradation, and you might have actually also heard about the Paris climate agreements, uh, there is quite a ban on establishing new coal power plants, and there is actually also uh, a campaign to shut down the coal power plants altogether. Even like currently, our Prime Minister of Pakistan, he have also said that there would be no coal power plants installed in a country. So that mean what would happen to coal itself? What would happen to the huge reservoirs of the coal which is present in the earth? So now that would actually mean like we have to utilize this coal in a clean manner. So there is a more research going towards the clean coal technology. And then there is another research, and that is actually another, I would say, like way to use this coal, and that is the integrated gasification of the coal. So, what actually integrated gasification of the coal mean? That the coal is converted to a gas, and that gas is burned into the combined cycle, and then electrical power is produced. So what is actually chemistry behind that is the, the coal gasification. When with the oxygen, it will give you carbon dioxide. So that is when the coal is completely burned. But now there is what we call it as a not a complete combustion of coal. So what would happen like um, three coal would be combined with the oxygen in the presence of steam that would give you H2 and 3CO. Sorry, C. This gas is called as syngas, or what we call it as synthetic gas. So this gas is further combined with the oxygen, or combined, in other words, it is actually combusted in, in a combustor to produce H2O and CO2, and that means like it is actually used in a combustion chamber to produce further energy, and then that further energy is utilized for the heating of the gas, which is expanding in a turbine, and so on the combined cycle power plant. So in this manner, most of the So in this manner, the coal is utilized in much cleaner manner, which mean like much of the solid waste is already gone or already taken out. Mercury is already removed, sulfur is already removed, particular matters are already removed from this coal, and the only we are left would be the syngas, which would be used in a combustion to heat the gases or the air which actually is there. The coal, if I would say like the hydrogen, which is actually made in syngas, it can also be utilized in other purposes. For example, making of ammonia, making, and obviously the now the most important hydrogen economy or upgrading the fossil fuel. It can still alternatively, like it can be converted into transportation fuel, such as gasoline and diesel, and with certain treatment and methanol and so on and so forth. So in this way, what we are suggesting, like the coal, which is actually not a clean technology or not a clean fuel, it is gasified in such a manner that it would be utilized in a further processes in a clean manner. This process is called as integrated gasification of combined cycle. There are different parts of this integrated gasification, um, and the most important is the gasifier. As said earlier, that the coal would be not reacting completely but partially with the oxygen. So there should be an environment in the gasifier which will only be actually providing energy, which will convert the carbon, or which would react the carbon into oxygen, not completely, but to produce carbon monoxide and H2. So this type of chamber is called as gasifier. For gasifier, we are supplying only and only oxygen, not, and that is oxygen from the air. So in oxygen, which is actually in the air, it is separated from the nitrogen in a separating unit, and obviously this air is actually moved into the air separating unit by help of a compressor, and that is the from the outside air, and that outside air is compressed into a compressor and then into pass into the air separating unit. And obviously there is actually H2O, which is actually required in terms of steam, or in a form of steam, and that is supplied from the HRB or the steam generator over here. So this is actually a process. Again, if I say like there is actually a part, what we call it as a compressor, which is used to compress air into the air separating unit. We can still say like by if we want to reduce the overall power plant cost, we can use this compressor over here as well, and that would be actually working our purpose. And also, like if nitrogen is actually extracted or from in the air separating unit, this nitrogen can be utilized it further, and also this nitrogen can be fed into the combustion chamber as well. And in the combustion chamber, we would increase the amount or the mass of the uh, air, and then obviously if the mass of the air is increased, so the power of the turbine is also increased. So this is all about integrated gasification combined cycle power plant. There is much more information available on the internet as well. There is much more information available on the YouTube site as well. So I would definitely encourage you to go through that one, and you would be having a much new knowledge about the IGCC power plants, and you would be having new technology about IGCC. I hope you understand this lecture. If you still have got any question, you can ask in a Google Classroom, or if it is permitted, you can pop it in my office as well, and you can ask me question. Thank you very much. Have a nice time.